independent of h bar, you can evaluate this, right? This would be like mass of the electron divided by m Planck square, or which is the same mass of the electron m Planck times L Planck. And this would be something like 10 to the minus, so this is 10 to the minus 33 centimeters, this is 10 to the 19 GeV, so MeV. So we get something like 10 to the minus 55 centimeters, okay? Now, of course, this is tiny, but it's still finite. Then you say, okay, so the electron has a mass, has an associated Schwarzschild radius, and it's point-like because it's elementary, so it must be a black hole because it is sitting somewhere inside of a Schwarzschild radius, okay? Now, this argument is a pure nonsense, okay? It's completely wrong, and this is very important to understand why it is wrong, okay? Now, you see, there are these type of simple statements that are extremely deep and important for understanding black hole physics. Now, the reason why this argument is wrong because it assumes that being elementary means zero size, and that's not true. Because being elementary only means that there is no substructure. When we say that the electron is elementary, we simply mean that it doesn't have a substructure. There are no entities, quantum field theoretic entities, which can be appropriately thought of as the constituents of the electron. That's why we say that the electron is elementary. But being elementary doesn't mean that it has no size. In fact, quantum mechanics is telling us that there is automatically the size associated with every form of a corresponding length scale associated with every form of energy, in particular a massive particle, right? So electron has this length scale, which is called Compton wavelength, which is simply inverse of the mass in h bar, with the times h bar, okay? Now, this Compton wavelength for electron, in fact, if you evaluate this, this is approximately something like 44 orders of magnitude bigger than its corresponding Schwarzschild radius, okay? So this particularly for the electron. Now, what's the physical meaning of Compton wavelength? You know this very well. Compton wavelength is a characteristic scale at which the energy of quantum fluctuations becomes as important as the energy of the electron itself, okay? So in other words, if you try to localize electron at distances much shorter than its corresponding Compton wavelength, you have to invest into the electron energy which is higher than the electron mass itself, and in fact could be much higher than what is enough for creating extra 10 electrons or whatever, okay? So this is the radius on which you are disturbing the system so much that it stops to be a system that you wanted to measure, okay? So for example, let's do this exercise for the gravitational radius. It's very simple. Suppose I want to do the following thing. I want to really build a microscope and try to measure, which will tell me that electron is definitely localized somewhere within its Schwarzschild radius, okay? Now, if I need to do that, this means that somehow I have to create a situation, or you can create a microscope, or in fact you can manufacture, if you are powerful enough with a lot of money, a lot of accelerators, you can manufacture the quantum state of an electron with wave function being localized, sharply localized in some distance within its Schwarzschild radius, okay? Now, so in either case, if you want to measure electron and say that, okay, electron is definitely within its Schwarzschild radius, you have to transfer the momentum to the electron of the order of h bar divided by the Schwarzschild radius, okay? Now, this means that you are disturbing electron so much that now the mass of the electron, the energy of the electron localized within that region, will be, actually, if you evaluate this number, you get something like the mass of Halley's comet. Okay, so electron will become heavier than the comet. Of course, this is no longer an electron, whatever it is. Okay, so therefore, now what are we learning from here is that the Schwarzschild radius of an electron is a fictitious scale. Okay, it's formal, you can define it. But there is no, you cannot never measure, there is no physics associated to it, okay, associated to that length scale, okay? So that's why electron is not a black hole. because the Schwarzschild radius, because the Compton wavelength of an electron is much larger than the gravitational radius of the electron. Okay. Now let's ask the following question. Okay. Now let me take an electron and do the following thought experiment: make it heavier and heavier. Okay. What happens if I make electron heavier? What happens is that you understand what happens, because the Compton wavelength is inverse of mass, and the gravitation radius is linear in mass. So making electron heavier, you increase gravitation radius and you decrease the Compton wavelength, and at some point they are going to meet. Okay. Now where is the meeting point? To see where is the meeting point is basically, well, you can use any of these expressions. For example, I can multiply and divide by this by G Newton, okay, and then I can rewrite this as so I will have G Newton here and G Newton here, right? This is the gravitational radius, right? And this is the Planck length square, right? So then this is Planck length, and Planck length divided by the gravitational radius. Okay? Now, these two, any of the two length scales can only be equal when all of them are equal, okay? So basically the meeting point is when the Planck length is equal to the gravitational radius and is equal to the Compton wavelength, okay? This is the picture. So now, so we can draw this picture like this. So this is the length scale. Let's say here we have Planck length here somewhere, and this is the mass. And then, okay, so the gravitational radius increases like linear. The Compton wavelength goes down.
그래, 프리즈가 난도가 좋다.
They meet at the Planck length. Okay, so this is the picture. So in other words, what happens is what this diagram is telling you is that this is the world of the elementary particles, okay, and then this is the world of black holes, and they meet at the Planck length. Okay, so at the Planck length, elementary particle is something in between. Okay, so it's not yet a fully fledged black hole. Why? Because the quantum effects are extremely important in all possible ways. Okay, but on the other hand, it's a very strongly gravitating object. So in particular, the particle with the Planck Compton wavelength, the corresponding alpha gravity is 1. Okay, for this particle, for a single particle even, and so it's literally in between. Okay, there are entities which sometimes people call them quantum micro black holes, or at least I call that way, or the boundary between black holes and particle, elementary particles. Okay, so now.